So we're going to do one more example of these Laplace transforms, and we're going to up the ante a little bit per se, and we're going to take a look at a second order differential equation. So now we have a homogeneous y double prime minus 6y prime plus 3y is equal to 0, and then we finally got into the point where we have one of these non-zero initial conditions. So y at 0 is 0, but y prime at 0 is negative 3. So let's go ahead and solve. First of all, what we can do is we can say Laplace of y double prime minus 6 Laplace of y prime plus 13 Laplace of y is going to be equal to 0. And the latter of the two terms we've already seen how to take care of in the previous example, so we know what those are going to work out to be. Those are easy, but this one we haven't seen yet, where we have one of these y double primes. So let's just focus on the ones that we know how to do. So we have minus 6 times s Laplace of y minus y at 0, and then we still have the 13 Laplace of y equals 0. And so this is the new term, the one we haven't seen before. And we can roll all the way back up to the beginning, and we can remember that this is going to be s squared Laplace of y minus s y at 0, and then minus y prime at 0. Okay, and again, we just go all the way back up, and we can look at that from our first rule, where the second derivative is equal to those three things. Okay, so what can we do at this point? We can simplify. Now notice that y at 0 is equal to 0. So anytime we see a y at 0, that term is going to go away. That's good. We also notice that y prime at 0 is going to be equal to negative 3. So here's how we can rewrite the next line. S squared Laplace of y minus negative 3. Right? So be careful with that because we want to make sure that we don't make a sign error there. Obviously, if we do, then the whole problem is going to be wrong. Minus 6s Laplace of y plus 13 Laplace of y. And that's going to be equal to 0. Right? Now, what we're going to do is we're going to factor out those three Laplace y terms. We're also going to subtract this positive 3 from both sides. And so our next line algebraically is going to be Laplace of y times s squared minus 6s plus 13 is going to be equal to 3. Or negative 3, excuse me. Right? And then finally what we can do is we can divide. And so our Laplace of y is going to be equal to negative 3 over s squared minus 6s plus 13. At this point, what we usually do is we look for the inverse Laplace, and that's exactly what we're going to do. So our final step to be able to solve, we've gotten rid of all the derivatives, as an integral transform generally does. And so now we're going to take the inverse Laplace. So we're going to have Laplace inverse of the Laplace of y is going to be equal to the inverse Laplace of negative 3 over s squared minus 6s plus 13. Right? Now, how do we take the inverse Laplace of that right-hand side? Well, there's lots of techniques that we can use that are at our disposal. All right? Now, on the right-hand side, the left-hand side, excuse me, that's just going to be y. Right? So we have y is equal to inverse Laplace of negative 3 over s squared minus 6s plus 13. All right? And let's try to go back through and think of some of the different techniques that we can use to be able to find the inverse Laplace. So one of them is just by doing some algebraic manipulation. We can multiply and divide by a magic number. All right, so we can multiply and divide by some constant or by some factor. All right. Another way that we looked at before, we actually saw this in the first two examples, was decomposition. Another way that was really sneaky was that we added and subtracted a magic number. So add, subtract some constant. Right. And one other method that we're going to utilize in this example is to be able to complete the square. And that's going to work really nicely for us in this example. All right. So one of the tricks we saw before was maybe completing the square in the denominator and then possibly using a translation theorem. All right, so let's rewrite y as inverse Laplace of -3 over s squared minus 6s, and remember we had 13? Let's rewrite 13 as 9 plus 4. All right, you might be thinking, well, how does that help us at all? Well, it actually does help us a lot because now what we've done is we've created ourselves a perfect square trinomial, and that's what we do by completing the square. We just break apart that constant. Now sometimes we have to add and subtract a magic number to make it work, but in this case we just go through and just break up that 13, and so y is going to be equal to inverse Laplace of -3 over s minus 3 squared plus 4. And you'll probably notice that this starts to fit one of the forms. Now, if this s minus 3 was just an s, then we could probably look at this like one of the sine functions, and in fact that's what it is. All right, we're going to have to do a little bit of doctoring with this. Okay, so what we're going to do is we're going to say y is going to be equal. Now I'm going to factor out the -3. Laplace of 1 over s squared plus 4 as s approaches s minus 3. All right, now this is going to be our k. So k squared is equal to 4, so k is equal to 2. And by now we've seen enough of these to probably recognize this as one of our either sine or cosine functions. So if the numerator had a 2 in it, then I think we'd be set. So what we're going to do is we're going to multiply the top by 2, and then we're also going to divide by 2 to make that equitable. So we're going to multiply by 2, and we're going to divide by 2. All right, and so this is now going to become y is equal to -3/2 inverse Laplace of 2 over s squared plus 4 as s approaches s minus 3. For our first translation theorem, a is going to be equal to 3, so we know that we're going to have an e to the 3t somewhere in the answer. This is going to be our cosine, or excuse me, our sine function, but not just sine of t, sine of kt, and remember k was equal to 2. Okay, so if you don't believe me, go back to that Laplace table that I provided for you in the previous guided notes. All right, so an answer, -3/2 sine of 2t, and then we're going to multiply that by e to the 3t. Right, and that's going to be our answer. Now, of course, we could go through and we could solve it using the old methods. Okay, so what we could do is we could try to find our y1 and our y2 values, or excuse me, our m1 and our m2, and then try to recognize it as a case 3 since it would have complex roots, and then we would just go from there. And I don't necessarily know if it will be any more or less work, because after we start finding the derivatives, substituting the values back in, we probably have just as much room for error in a sign error or computation error. The difference is with the Laplace transforms, it's a little bit higher level thinking. Although if you get really good at these, then you can start taking some shortcuts, and you can start recognizing the patterns very quickly, and you won't have to do so much rote computation to go through these. Okay, so in our last example, which we're going to see in our next video, we're just going to go through and we're going to take a look at a non-homogeneous second order differential.